Today we jump from a lot more algebraic approach to a combination between algebraic and geometric. And we're going to jump into trigonometry. And trigonometry talks quite a bit about angles. Just for definition purposes, we know an angle is two rays from a common vertex. And the ray that you start at is called the initial ray. The ray that you end at is called the terminal ray. And the space between is called the angle. We're going to notate our angles with this symbol, theta, which is basically another name for x, but this is a geometrical universal term, I guess, to determine an angle. Now, two types of angles that we can talk about are positive angles and negative angles. So let's say I've got this blue angle here where I'm drawing something like this, and let's say theta is equal to, let's say, 60 degrees. Now, if I want to measure from this initial ray, and I say this is the initial ray, in this counterclockwise fashion, that's a positive 60-degree angle measure. Now, let's say I was to draw an angle again with the same terminal ray in green and go here, and I told you that this was 30 degrees. This isn't really 30 because we're moving in a clockwise fashion. This would be a negative 30-degree angle. If I was to go positively, that would be a completely different measure. So depending on which way you rotate, in clockwise or counterclockwise fashion, that's going to determine positive and negative angles. Two rays that have the same terminal ray are what we call coterminal. So in this case, I'm giving an example of 270 degrees. Now, what we're going to find often is that we're going to have our initial ray pointing in the positive x direction, okay? And this is called standard position. Basically calling our zero position here. All right, now if we want to go 270 degrees, we know a circle is 360 and every perpendicular quadrant is 90, so 270 degrees is down here, and we would rotate in this counterclockwise fashion and call that 270 degrees. This is my terminal ray. Now, if we could do 90 degrees, but in the negative direction, that's like going like this, but it makes the same initial and terminal ray. It's just dependent upon which way we rotate. Now, clearly, this is rotated bigger and the angle opening is much bigger than it is here, but we start and end at the same place, so these are coterminal. Now, we want to know, okay, what are some coterminal rays for these three angles here? Well, 181 degrees is somewhere over here. And that's when I rotate in this counterclockwise position. So now, if I want to rotate the other way and go here, I'm 1 degree short of 180 degrees, all right, which would be 179 degrees. Of the negative type. Now, that's not to say that's the only coterminal angle. There are infinitely many coterminal angles. For instance, I have 181 and negative 171. Well, what if I was to take, and instead of just going to 181, I was to go all the way around the circle one more time. So instead of stopping here, I continue to go all the way around. And when I do that, I find myself back at the same spot I was, which is the definition of a coterminal angle, and I'm at 541 degrees. And notice I've gone all the way around the circle, so if I was to just add 360 degrees, I get to that next coterminal angle. Likewise, if I was to go the other way, I would get to another coterminal angle. So In order to get a coterminal angle, basically you add or subtract 360 degrees to get next coterminal angle. So here we go at 562. If I decide to get a positive angle that is coterminal, I could just go all the way around and subtract 360 degrees, which would get me 202. So 202 degrees, here's 180, another 20 and 2, puts me somewhere right around here. But notice this 560 was obtained by doing this, whereas the 202 is obtained by doing this. And they're both coterminal because they start and end at the same terminal rate. Likewise, if I want to take negative 456 and go around 360 degrees, that would put me at negative 96 degrees, which puts me somewhere around here. And I got that again by adding 360. And there's my negative 96, whereas rotating around 1 and a little bit more times gets me the negative 456. Up to this point, you've measured your angles in degrees. Well, today we're going to talk about radian measure. Now, an angle's measurement relative to the distance around the circle, or kind of like an arc length, like so, this part out here is what's known as its radian measure. Now, circumference we know of a circle is 2 pi r. We're going to talk a lot this year about something called a unit circle that has a radius of 1. And the circumference of a unit circle is 2 pi since r is 1. So 1 revolution all the way around is 2 pi radians. Now, again, this 2 pi would be similar, if you will, to 360 degrees. That is kind of like its equivalent degree measure. What we're going to do is we're going to take a look at the similarities between degrees and radians. We just said that this was 0 degrees, or it could be 360. And we just said in radians, if this were a unit circle, which we're going to deem it as, we'll say this radius is 1, is going to be 2 pi. So 360 equals 2 pi. Now, if I go halfway around a circle, that's 180 degrees. And if I've gone halfway of its radian measure, that would be pi. Now, if I take and I've gone halfway and I go another half of 180 is 90, and then half of pi is pi over 2. So these are all equivalents. Let's go just 30 degrees around. How does 30 compare with 180? Well, it's a sixth, so it must be a sixth of pi. Likewise, if I look at 60 degrees, 60 is a third of 180, so it must be a third of pi. If I go to 45, you'll notice 45 is a quarter of 80, so this is a fourth of pi. And you could do this forever and a day. But let's continue to go around and just talk about some other different angles that we're going to use a lot. So if I keep going by 30s, I can keep adding a sixth. Notice 1/6, 2/6 is a third, 3/6 is a half, 4/6, adding another 30 degrees, is 2/3. Adding another 30, I get to 150 and I get 5/6. 6/6 is pi. Adding another 30, I get 210, or 7/6. Adding another 30, I get 240, which is 8/6, or 4/3. 9/6 is at 270, but 9/6 is 3/2. 10/6, adding another 30, gets me to 300. And 10/6 is 5/3. 11/6 gets me another 30, which is at 330. All right, and all I have to do now is really fill in my 45. So there's a quarter, 2/4 is a half, 3/4 is 135, and 3/4. 4/4 is 1, 5/4 it's 225, 6/4 is 3/2, and finally it's 315, and that's 7/4. So you should be able to intuitively go around and look at these equivalents between radian and degree measure. Now sometimes you're not going to have super clean fractions, and just for study's sake, if you want a cleaner copy, here you go. But again, sometimes you won't be able to necessarily have super clean fractions, so you might want to have a formula to do a conversion with. And there's a direct proportion that does this conversion for you. You take the radian measure over pi is equal to the degree measure over 180. So if I want to just do some grinding algebra, all right, I can go ahead and do this. So this is a degree over 180 equals a radian measure over pi. I get a reduction of the zeros, so that's 7/18. And then multiply pi to the other side, and its radian value is 7/18. All right, now if I want to go 248, I just take 248, put it over 180, again, r over pi, 248 over 180 reduces to 62/45. Pi. Pretty simple. Then we can go back the other way. I have 5/8. That's not something I saw on the unit circle. That's 5 pi over 8 over, that's a radian measure, pi is equal to the degrees over 180. All right, and the pi's will reduce, which means I just have 5/8 times 180 to get my degree measure, which in this case is going to be about 112.5 degrees. 11/4, that's also not seen on the unit circle. However, we'll talk about that after I get done with this conversion. We'll take 11/4 pi, put it over pi, and set that equal to the degrees over 180. And we have 11/4 times 180, which is equal to 495 degrees. Now, something interesting about this, let's just take and draw a quick circle here. Say it's a unit circle, and I'll put some crosshairs in here, like so. Not great, but it's close. And 11/4 is really, if I do a little quick division, I've got 2 3/4 pi. I could find a coterminal angle to 295 real quick, or even to 11/4 pi, because here is 2 pi or 8/4. And if I go 3 more fourths, there's 1, 2, 3. Notice what I get to. I get to 3/4 pi. That's a coterminal angle. And that's also equivalent to 11 pi over 4. Now I want to know where 1 radian is. Now, the common misnomer is that 1 radian is right here. But that's equivalent to pi. That's pi radians. Well, how much is pi? Pi is 3.14. All right, so right here is 3.14 radians. This is pi over 2, which is half of 3.14, which is about approximately 1 point, I'm going to go 57-ish, right? So 1 radian is somewhere in this first quadrant over here. So just understand what we're talking about when we're talking about a singular radian. 2 radians is here, 3 radians somewhere over here, 3.14 here. This is 6.28 radians, or 2 pi, as we've talked about. So now we want to find some coterminal angles, 5 pi over 3. Well, 5 pi over 3, we looked at that before. We can go in thirds if you want. Here's 1/3, 2/3, 3/3, 4/3, 5/3, right? And that's going in the positive direction. Well, if I want a coterminal angle, all I have to do is go from, this is 6 pi over 3, back, and I can say coterminal is negative pi over 3. Negative 3 pi over 7. This is roughly 3.5 pi over 7. Negative 3 pi over 7 puts me right here-ish. Now if I go a full pi, again, this goes this way, I want to know what this angle would be. A couple ways to do this. I can do it intuitively, saying that there are 7 pi over 7 in 1/2 rotation. I need to get another half rotation, which would be another 7, but if I back off 3, that's another 4 pi over 7 to get here. 4 and 7, that would be 11 pi over 7 in terms of a coterminal angle. Or what I can do is I can take the negative 3 pi over 7 and add 2 pi to that. Well, 2 pi is the same as 14 pi over 7, which is 11 pi over 7, as I explained more intuitively. Being able to do it both ways is probably real helpful, because you don't want to necessarily be calculating your life away when you can just kind of think about it in your head and geometrically what's going on. All right, we started by talking about radians in terms of arc length. Let's just kind of define what arc length is. You had this last year. S is known as the variable used for arc length, and that's the distance from one point on the arc to the other, and that's equivalent to r times the angle. But this angle has got to be in radians. All right. Likewise, if I want the area of this sector, all right, so I take this piece of pi out or piece of pizza out, all right, that sector area is equal to 1/2 r squared times theta, where again theta is in radians. So most of these problems are just plug and chug. Let's do just a quick one. We want to find an arc length, and the sector area of a circle has a radius of 12, and then 40 degrees as its angular measure. 40 over 180 equals r over pi. That's 4 pi over 18, which reduces to 2 pi over 9. Multiply that together like so, and get our units. Actually, this will be in centimeters, right? And that's my arc length. We take a half, the radius squared, multiply by 2 pi over 9, and we get our sector area. All right, like I said, plug and chug. And that'll do it for today. We will talk to you next time.